So what triggered this particular the topic is the following, that usually every summer season before the rainfall starts, right, monsoon starts, we talk about what will happen this year. And usually people will go to some phenomenon. Usually people will say, and so will be this like this, or IOD will be like this, and whatever. North Atlantic will be like this, North Pacific will be like this, right? So we tend to see the entire season as an entity, one single mechanism, right? And so we'll do this or whatever, maybe something, right? No matter what, right? So can there be different mechanisms during different parts of this season? That's the one I'm talking about here. So for that, we have to define this seasonal cycle first. So this is the seasonally average daily rainfall, basically seasonal mean climatology of rainfall over India here. This is from the graded data set and this internal standard deviation. And this is the opportunity to even promote the book. It is taken from this particular book. So now there is mostly homogeneous rainfall rate, but moderate over central India, large region here. Low rainfall over this northwest side, but very high rainfall again over this region. What is that other thing is there? No, not least that. That is out. Okay, I'm talking about this windward side has a very high rainfall. Even the windward side here has very high rainfall. The windward side of the mountains, and this is spatially homogeneous region. And typically, the standard deviation, the internal standard deviation of that every year's average is proportional, kind of proportional. Higher the climatology, higher is the internal standard deviation, which goes typically with this kind of a quantity where there is not zero. Okay, I mean, it is the many times it is zero and there is only positive values are there. But such a rainfall, the seasonal rainfall, does not come in a particular day, right? It evolves throughout the season. So what I plot here is the shaded is the net energy input to the atmosphere. That is at the surface and the top of the atmosphere, net energy input to the atmosphere. All these regions are positive and these greenish regions are negative. Now this is in May. On top of that, we have plotted the hatch regions are the P1, the very high total precipitable water in the atmosphere, say about 50 watts per meter, 50 kg per meter square, higher value. And the contours are rainfall, high rainfall area. So things to notice is that in May, where the location of the highest net energy input to the atmosphere is the South Bay of Bengal or Equatorial Indian Ocean, it moves in June over this region, July again towards this region, August tilted, September comes back, October again comes back here. Right? But, yeah. Now, associated with this high net energy input to the atmosphere is the high amount of precipitable water. Sometimes it slightly lags, but most of the time it leaves here. But it is around that high value of precipitable water is around the region where net energy input to the atmosphere is the highest. Okay. Rainfall, again, initially it need not exactly follow the region of high net energy input, but during June, July, and August, look at it, it kind of it is little northward side of the regions where the net input energy to the atmosphere is positive. Okay. Now, the difference again, look at the June and September, where this is the month of the onset phase and this is the month of the decline phase or the withdrawal phase. The net energy input are not symmetric. Look at the North Pacific Ocean here. This is negative in June, but in September it is all positive, right? Over this Yeah, Bay of Bengal and Arabian Sea is strongly positive in June, but becomes very weak, weakly positive in September. All right. So even when the total rainfall over India during June and September are close to each other, we know it. But the total or the spatial distribution of the energy input to the atmosphere in and around are not same. Right? So this gives us the possible hint that the mechanisms that drives this rainfall versus this rainfall could be different. Why? Because in a steady state, if the atmosphere need not heat up or cool down anymore, then the circulation of the atmosphere, vertically integrated circulation of the atmosphere, should take away this positive energy that is coming in at the surface and at the top of the atmosphere, right? So this may drive, this positive energy input may drive the circulation, and the circulation in turn may change the surroundings like SST over other regions, and that gets feedback. But nevertheless, for the timing, let us consider that the necessity of a constant temperature atmosphere is the following, that that positive energy will get diverged from by the winds, vertically integrated winds. All right. So therefore, winds will be driven, winds will be different here compared to here. Now, this is the daily rainfall climatology over Indian land region. This is the typical region which you have. You have much sharper positive growth of rainfall during June and all the way up to the beginning of July. Then it stays and then slowly comes down. This is the very, very strong seasonal cycle. And about 80% of the total annual rainfall happens from this date to this date, about 80%, isn't it? So that is known. But if this every year, it doesn't follow the same thing. There are internal variations, and then the daily internal variation would be very, very large. So thus, what I did is that I kind of averaged every 5 days of rainfall, and then I took the internal standard deviation. So this line is basically standard deviation of pentaid mean rainfall multiplied by some numbers. Okay, to get this one. So what you can notice now here is that beginning that during June, even when the rainfall is less than, say, for example, this time, the internal standard deviation is quite large. However, it is largest during the end of June, right? Where kind of the entire India sets up with the rainfall, seasonal mean rainfall. Okay, so that onset date, mean onset date after 15 June is here. This is 15 June mean onset date after 15 June is here. So this is the time here. So you get the highest internal standard deviation of the all India summer monsoon rainfall, right? So now, what can happen? The problem is that such a strong seasonal cycle with a strong internal variation, especially part of the season, right? Part of the season kind of says us that there are strong interseasonal variations, right? And which is kind of known. Like here, right? Here is going to characterize an internal standard deviation, which is kind of, I think I have gone backward. So what I try to say is now, it is difficult to perceive from these figures that with a strong seasonal variation, that the different parts of the summer months will be forced by different mechanisms. It's very difficult. This looks like a very solenoid one. The entire season is such a solenoid. Okay, it's very difficult to understand. And as yet, observations indicate some other story. That just from observations, something will come here. Oh, something is going backward. Now it is. So this is the daily rainfall. The green line is during 2002. Okay, I mean, it is very, very well known that there's a very strong drought during July. Okay, just 1 month lesser than I've chosen this. This is the climatology again. And the rainfall anomaly during July of 2002 was minus 60%. Minus 60% of rainfall of the climatology. Now, what happened because of that? Sorry. So what I tried is that this total rainfall, now it requires moisture. And the moisture comes from different parts. This is FW is basically over Arabian Sea. That means comes in usually positive. This is positive here. FS positive and FN positive going that side, right? So what I plot is the fraction of the FW and all these quantities, including rainfall, during July of 2002. So this means that 40% of the climatological rainfall happened in July 2002. That's all it is. Okay. Similarly, this means that the FW, that as much moisture came in, it was about say 90% or 87% of the seasonal of the climatology of July. Similarly, FE is about 1.1, more than 100%, more than 120%, and these are all very, very close to zero. Okay, so that total F net is the net total net moisture convergence, which was very weak, about 20% of this. So the take-away message from here is the following: that even when rainfall was only about 40% of the climatology, the incoming moisture flux was not that low. It was it was lower than normal, but it was close to 85 to 90%. Okay. Now, therefore, this much of flux or the moisture was available, right? So that if the conversion rate, if you call that as much moisture coming in and it rains with proportional, then rainfall would have been about this percent itself. That did not happen. So what happened basically, most of the moisture went out, right, through the FE. It just drained out, right? And F net, that is the net moisture convergence, is even weaker or less than the precipitation fraction. That basically suggests that this F net there is some other mechanism that even with that amount of moisture available, it rained more than what it should rain only through the proportionality of F net. That's basically it suggests. Now, just an example, again, because I'm all talking about seasonal cycle. This is June of the same year. All these quantities, have a look at it. Rainfall was close to normal. FW was close to normal. AE was close to normal. F net was a little high. Sorry, not this is FM, but don't worry about it because actual value is very low here. This is this Himalaya is there. So this is by division it became very, very high. So it does not contribute much to F net. Okay. So June, it was all close to normal. August, again, it is all close to normal. So just 1 month in between, that was highly anomalous. Okay, just 1 month. And there are possibly many other cases like that. Only the difference is that in this particular year, it kind of followed a calendar month. Some other year, it may be half or part of it for 1 month, another part in another month. Okay, but even then, this is a very, very unique situation of July 2002. Right? Now, it kind of indicated us that the mechanism that gave us rainfall in June of 2002 would be very different than July, and then possibly again different in August, right? So therefore, there could be monthly differences or monthly variations in the mechanism or the dominant mechanism. And the literature says something, right? That it is not that literature do not have all those steps. So, for example, one of these earlier paper by Pascal too, he showed that how the early and late summer monsoon seasons be modulated by Indian Ocean SSTs. Especially he spoke about here the late summer monsoon season. So what he's talking about is that a positive SST anomaly in winter to summer here. So it starts developing in winter because of El Nino or Indian Ocean dipole, but not here. This is South Indian Ocean dipole here. That happens here. So there's a positive SST anomaly here, pushes the climatological location of the masculine high towards northwest, right? And because this is southern hemisphere, the winds are anti-clockwise over this region, right? So that kind of enhances the cross-equatorial flow, which is climatologically comes here and goes here. So this enhances the climatological flow and then enhances the moisture flux here. So more moisture availability, that kind of enhances the Hadley cell and gives a feedback, right? So what he's talking about this entire system may not only triggers this high rainfall over India during the late monsoon season, but also maintains this kind of condition and may develop El Nino La Nina in the near future, or that during the late season of late summer monsoon season or the coming winter. That's what he is talking about. So he is talking about August, September, or the late half of the summer season rainfall. Okay. Now we have also done here for another indication that with Gaurav's work, what we found is that impact of ENSO in over for July and August rainfall was very different before 1980s, and it could become exactly opposite after 1980s. So it will be little more clearer if we show this plot that in recent time the July rainfall is more affected by ENSO than earlier, and in earlier before 1980s it was August rainfall was slightly more impacted by ENSO rainfall than today. So that now ENSO and rainfall, actual monsoon rainfall is basically positively correlated over the central Indian region at least. Then we tried to show some mechanism here, and we showed that it is basically dependent on how the ENSO impact the mid-latitude temperature anomalies at the middle upper atmosphere. That kind of drives the winds and the northern propagation and blah, blah, blah. Okay. So there is some mechanism here. Another work which I did some time ago, that I don't know where it's to this one, but it basically takes 4 SST regions around the globe and tries to do a regression model and shows that using only SST over these 4 regions, you can explain a very large variability of the internal variation of the June and July rainfall, right? But the problem I think here is that this particular regions of SST cannot explain the late summer season, that is the August and September rainfall. Okay, so basically again indicates that it does not work because different parts of the season may have different mechanisms. Another indication is here by Venus this one work that what they showed is the non-El Nino droughts, which is the blue line, is basically when the August rainfall was very, very low. So that El Nino droughts, when the July rainfall is low, but the non-El Nino droughts, August rainfall is low, right? Again, the difference again that what it indicates, there is no mechanism, but I mean, there is no mechanism. They have some mechanism. I'm not talking about that. What I'm saying is that there is no mechanism in terms of the different parts of the season, that it does not say that why, for example, this won't impact the June rainfall or July rainfall. Similarly, this particular work, what I showed here, it does not say, I could not say here that why this SSTs cannot explain the August and September rainfall variations, right? So in summary, although we have some idea that different parts of the monsoon season may be driven by different mechanisms, the actual mechanism, especially if we ask the question why there should be difference, is really unknown, right? Why there should be a difference. There are bits and pieces of mechanism that works this part and that maybe works another part. But the reason of why is to ask the question or to answer the question, we try to look at the something following. Start from the synoptic scales variations, high frequency variations, and low frequency ISO variations of rainfall over central India. Okay, these are the typical mechanisms of industrial variations of rainfall. And you look at the climatic variability of rainfall of different bands over this one. So what it basically suggests that at the synoptic scale, very high frequency, you have a strong seasonal cycle. Okay, June, July to August to September, right? High frequency oscillation, that is 10 to 20 days, which is basically the equatorial loss waves come from the West Pacific to Indian region. There is no seasonal cycle, it's flat. Okay, and for this low frequency variability, again has to some extent some seasonal cycle, although weaker than the synoptic scale variations. Okay. Now, in the state of the rainfall, if you take the winds at 850 hectopascal over India or over central India and do the same analysis, you do not find any seasonal variation for the synoptic scale. It's flat. You get a seasonal variation for the low frequency variability time scale, right? So basically suggests that the synoptic scale variation which we found here in rainfall is not associated with the synoptic scale variation of the 850 hectopascal winds. But please note that at the synoptic scale, the winds are very strong, right? Winds are very strong. So if this flattened wind would have been the only mechanism to have the rainfall at the synoptic time scale, then also you would have got a flatter variations of these blue bars. That doesn't happen here. So, however, if you look at the seasonal variation of P1, there's a strong seasonal variation here. So this is from June to July, August, and September. So, and to make it a little better here, if I just put it together, this is the synoptic scale bar which I showed before, the blue before, and this is the P1. So kind of matches. Again, what it suggests is that if you have to have, so the synoptic scale variations is correlated or it's dependent on the amount of PWatt available in the atmosphere. If you have higher PWatt, you are going to get higher variations. But it is also associated with the winds. However, winds variations are always present. Okay, so only when you have PWatt, it kind of enhances it. Actually, rainfall kind of when it happens. Now, the mechanism that drives different interstellar oscillations are different because we now saw there are different seasonal cycles. The mechanisms are different, and ISOs depend on not only a local but also as a remote factors. People have shown that various times. And Indian region experienced considerable internal variability at the onset date. For example, from our lab itself, we showed that for central India, there are considerable differences in the early and late onset over regions. And that again depends on various factors like surface pressure over India, over different regions. So, is it possible that the monsoon rainfall during the early and latter parts of the season are driven by different local and remote factors? Why does it come now here? Because if the rainfall is dependent on the synoptic scale variability depends on the PWatt, you must have a connection between PWatt and the rainfall. However, PWatt itself should be driven by the large scale factors, including temperature and the moisture convergence, right? Therefore, large scale winds, right? So that given this particular idea, we have done a recent study from the department, and this have a look at it here. So we have this is plotted the cross correlation of the rainfall during different months with different months. Okay, so basically this is May with June, and so on so forth. The September with July, right? So we have a look that June rainfall is basically weakly correlated with many other months, July and August, even September. There is no significant correlation. What happens is that July and August rainfall are highly correlated with the September rainfall and even with the October rainfall. So it basically suggests that this rainfall during June is kind of uncorrelated with the latter part of the season. But the latter part of the season are kind of more coherent with each other, right? At the internal time scale. All right, July, August, September. So that must come out with some kind of mathematical analysis. So to do that, we have done empirical orthogonal function analysis of the monthly rainfall, internal variations, and for different years. So this is here. So this is the first mode, and this is the second mode. So the first mode, again, if you have a look, there is in June there is no variance. July, August, and September and October have a high variance, saying that these 4 months are together. And the first and the second mode have a positive value in June, then July negative and kind of dampens with oscillatory damping behavior. Okay. What happens is, if you look at the time series related to the first mode, which was, if you please map there, the first mode, that is tau, I call it here, the time series. If it is positive, then the rainfall over India was higher. Okay, and for the second mode, if it was positive, then June rainfall was higher. So if the first mode, if I take the internal variations, and if I do a correlation or the regression with the, I think it's a correlation, right, with the global SST, then what we find is that from previous December, January, February to August and September, we see a strong signal of developing ENSO, the first mode, right? However, the second mode has very weak signal over the equatorial Pacific Ocean. So noting that the second mode do not have any connection with the ENSO, flatter. But the first mode is connected with the developing ENSO, right? Is weaker in even June, July as compared to August and September, right? So this is even more prominent or evident here that with correlation of the needle frequent SST anomaly with the first mode is weakly positive during in early summer, winter, early part of the year, and then kind of drops down here. But for the second mode, which is here. So now if I go back and just remind it here that the first mode is related to the rainfall from July to September, but the second mode is related to the rainfall in June and again opposite phase in July and so on and so forth, right? So therefore, the onset phase now, therefore, which is that second mode is not related to the ENSO. To understand that, therefore, what drives it, we have filtered out the precipitable water and we had also winds also. So this is the precipitable water related to the latitudinal oscillation and shows that for the years when the June rainfall was very high or the first mode was very high, the precipitable water related to the latitudinal oscillation moved from west to east and as well as from south to north and covers the Indian region, developing the water vapor over the Indian region. Okay. And this is also related to the onset dates. Similarly, for the first mode, when the first mode is very high, second mode is very high, that onset mode, the onset over central India as well as the northwest India is earlier compared to when it is not high or the first mode is lower values. So indicating that an early onset is given this. Now, what would make this, what will be the mechanism for this moisture flux? We did this before in terms of the surface pressure anomalies over Indian region, and kind of it suggests that your low level moisture flux can be related with the meridional gradient of the surface pressure of these two boxes for FW and these two boxes for the FE regions. And now for this particular case, we found again that when we have droughts over India related to ENSO, the surface pressure anomalies are asymmetric in the north-south directions. For example, over Arabian Sea here, this is India, this is over Arabian Sea, the surface pressure anomalies increase from south to north. But over Bay of Bengal or in the Maritime Continental region, surface pressure anomalies decrease over south to north. However, when you have non-ENSO droughts, over both these regions, there is an increase in the surface pressure because please note that this is more weaker, that the anomaly is even less than compared to here. So in essence, the El Nino related droughts are related to the wave flux going out and here and going out more here, but non-El Nino related drought is flux is in the one direction. So this is zonally asymmetric, this is zonally symmetric. Okay. So this you have tried to now connect with this particular that work which you have done. We have shown now for the high minus low out years, basically high when the rainfall over India is high minus low. In June, the pressure anomalies are much higher, but quickly higher, but closer to the equatorial Indian Ocean, which kind of makes this anomaly gradient negative here as well as negative here. But in July or September, latter part of the season, it is positive here and this is negative here, which I do in the next plot. That in June, in 50 to 70, that is our Arabian Sea. This flux is here, so decrease westerlies because of this, decrease westerlies because of this. So these two, both of them decrease. There will be no net effect. But in July or September, the decrease westerlies here over this region, that Bay of Bengal, but increased westerlies over the Arabian Sea makes the moisture conversion stronger, and there will be higher amount of rainfall over Indian region. So basically, this is a symmetric variation. This is an asymmetric variation. So in essence, from June to July or September, the entire climate changes from a zonally symmetric condition to a zonally asymmetric condition. And the difference is not over the Bay of Bengal or West Pacific Ocean, but the difference is over the Arabian Sea region. The difference between June and July is here. Sorry, not here, but here. This changed the gradient completely over this region. So now that we have understood that it is the latter part of this rainfall season that kind of connected to ENSO, but the feedback between ENSO and rainfall over India cannot be ignored here because there must be a positive feedback. So to do that, I've taken a plot from the book by Wallace's recent book. What they show here is the SST anomaly over below 3.4. This is the higher the rain years, higher the SST anomaly. And these are different months, January to December here. So this is basically boreal winter. Again, this is boreal winter. And these are all for the warm anomalies, and these are all for the cold anomalies. Things to notice here is that highest anomaly of the SST you get during the boreal winter season, October to January. Again, even for the cold anomalies, October to January. Right? So the ENSO, that is kind of well known, but it's a different way of showing this. ENSO peaks during boreal winter season. So a recent paper by Tuckman, they wanted to understand that why such a seasonal cycle of ENSO. What they showed is that for West Pacific, the SST seasonal cycle shows that it is highest during September, October, November. But over East Pacific, it is in the March, April, and May, right? And this is around the same thing here. And here there are markers on the monthly SST anomalies, and shows that most of the strong ENSO years happen during December, January, and February. December, January, October, November. So the winter specific, that this one, right? So they did 2-3 experiments, basically 2 experiments. One is with the aquaplanet model without any continent and under with an aquaplanet model, but they have put a continent type of stuff, Eurasia continent here. And finally, they show that only when they have the continent, that is the red line, they could reproduce the seasonal cycle of SST anomalies both over West Pacific as well as East Pacific Ocean. Not just that, they showed that the number of ENSO events that peak during December, January, February is far more when the continent is included as compared to when it is not. That is only flat aquaplanet. So basically suggests that the Eurasian continent is important and the monsoon over this region is important to drive this observed seasonal cycle over both West Pacific and East Pacific Ocean, as well as the seasonal phase locking of ENSO. And then what they say is that they explain it through the particular mechanism, where they say that because of the presence of the continent with a high amount of rainfall here, the energy of this air becomes high, that when it goes to the West Pacific Ocean, it kind of reduces or freezes the evaporation of water here. That kind of keeps the West Pacific warmer. And that in time, a few months, it becomes higher, right? And that kind of creates the Walker cell stronger, right? Stronger winds and stronger upwelling in the East Pacific Ocean. And that again decreases the SST of the East Pacific Ocean. That kind of mechanism they have shown. But then we have looked at it here again with Sujata, we are trying to do something. This is their definition of West Pacific. Okay, and all in aquaplanet and everything. So look at this. This is the moisture flux also. So there's hardly any wind from the west over this region. So all the west easterly, there is a strong positive pressure here with high pressure anomaly here related to that winds are here. No matter which month you go. I mean, especially in there will be slightly here in August, there is a little bit here, but not in June or July, especially. Right, so there are some, there could be some issues with the configuration that with a flat, ocean and with some idealized continent versus a very, very realistic condition. Okay, so what basically it suggests is that the mechanisms driving early and late summer monsoons are different, and onset is driven by NGO, and once water vapor is built, ENSO's impact becomes profound. Only when the water vapor is high, ENSO starts impacting. Otherwise, ENSO has no impact. So ENSO-monsoon interactions further would modify each other's seasonal evolution. So what is that now? The take-home message is that early and late summer seasons may be defined based on the physical mechanisms. So it should be defined by the physical mechanism, not by the calendar months. This division would not follow calendar day and will be different in different years because it depends on the time when onset happened, for example, in this particular case, right? Once the onset happened, we can say we may start the second phase of the season. If you define this particular way, there could be many other ways of definition. Okay, so this is only this one. I think 45 minutes over, right? Or something. Yeah, 40 minutes over. I think it's okay. I think maybe another day I'll continue. Yeah, we have any question?
The first plot you showed, he names standard deviation on rainfall over the land.
Okay.
So, what the ocean, how does is it more uniform or the ocean during the monsoon rainfall?
Rainfall you are talking about, rainfall, right? So you do not have rainfall over Arabian Sea much during this time, but Bay of Bengal starts in, this one, right? Yeah, so this patch will get extended here and you get very high rainfall here. Very high rainfall, but that starts even in May itself. Moisture came down. So it need not be linear with moisture. That has to be definitely has to be seen. Moisture came down because of the outgoing flux. You look at this. This is interesting actually. So you look at this one, no? So look at this. F is what is going out. Okay. So although about 90% of the climatology came, but 125% went out. Okay, that decreased the net flux.
What mechanism why it did not rain?
Oh, why did not rain? Uh, that's difficult to say. Okay. Well, one of the reason is definitely decreasing the total amount of moisture, and it is not linear because moisture amount availability itself is it's not only it also changes the stability of the atmosphere. So it is only from the pure perspective as well as stability around atmosphere perspective, right? So stability will increase non-linearly with a decrease in the moisture, right? Now there could be some international oscillation that came. Those are different things. Question is why locally it decreased. Possibly it can be explained by the amount of moisture, and its impact on the stability of the atmosphere.
Can we say high wind?
Correct. That's the thing. So it was an El Nino year. So for some reason, this particular month, it kind of affected out. But again, there is no explanation that why in the next month it came back. Isn't it? Again, it could be related to some interseasonal, this one. Okay, convergence and all this. Well.
So here in June and August, if we see the AFNET and precipitation are proportional to each other, like
Yeah.
kind of, but why this in July differed so much? Like AFNET is about 0.2, but precipitation was 0.4. Like there is this issue of as well. Like, what can you say about that? Why is it?
Yeah, I would say there is a mistake here. Okay, mistake in the sense that mistake in terms of the representation. Okay, the FNet what I calculated over the entire box, but the rainfall is only over the land region. Okay, so it is very highly likely that during a month when the rainfall was so low, the FNet as well as rainfall was patchy over the entire domain. So they won't go to each other. Okay. So we have seen this in a model. If you take a model and the relationship between FNet and rainfall is far more linear or stronger compared to in the observation. So there is no perfect this one here. And I would think it is this way. But there is another reason that is like you cannot always say it is proportional to the rainfall because FNet is related to the it will change your P watt, right? And with a very low P watt, your rainfall is kind of insensitive to the P watt value, and high P watt it exponentially increases.
So it's usually like materially over the levels. What is the problem there? Like it's part of the atmosphere's moisture component, maybe more contributing to moisture.
This is integral, vertically integrated. No, so I don't think it is the upper level with this one. Okay, so because the moisture actual amount is so low there. Okay, so I mean upper level will have an impact, but it may have an impact in different way. It is important. I'm not saying that, but in this particular case, when you're talking about P word, it's mostly will be driven by the low level because of the sheer presence of the value. Okay.
One question here. Are these anomalies actual values? Because
This is a fraction.
this cannot be greater than this. Fibonacci is negative, not possible.
No, this is a fraction of the climatology.
Oh,
So everything is divided by its own climatology.
okay.
So this is that basically this is FW is 80 or 90% of the climatology of FW.
Okay.
So that's the thing. So this P minus is will be positive only here because FNet is positive. I mean, actual April is positive, climatology. This month, divided by April is positive, basically says that this month also was positive because it didn't become negative. So they are copying.
But then, to the actual value, what do you want?
No, I have the actual value also because I wanted to show.
Because it was so interesting, I would like to know how much higher Fe was in actual millimeter per day. That will give me the, because now and then by climatology it causes confusion.
Yeah, it's
I'm
like.
not looking at it because that is a very peculiar month, July 2000.
Yeah. Yeah, that's I can do that. This,
Yeah.
fine.
Thank you. Yeah, I can see that monsoon is almost reached its end point here. I think today is not well, it's somewhere here. So onset process is completely over. Okay. And I looked at the condition at noon today from Windy's current data and forecast by GFS. And this is a snapshot, this is not average. So you can see that GFS forecast is not very good. Okay. It doesn't get all this big system here. Okay. It doesn't get this system here. Of course, this is cloud top temperature, this is rainfall. We argue that they're not same. But still, it's surprising that such a big thing over probably Punjab is not seen in this forecast. Okay. So I think there are problems with the forecast. Okay. If you look at cumulative rainfall, data of the 24th, and we added just now the 25th value. So as of today, rainfall in June is higher than climatology. We have crossed into the positive. So June rainfall most probably be normal, but will not be above normal as many people had predicted, many models predicted. Okay. Now I just want to make a comparison between Kerala and Karnataka. In Kerala, I'm impressed that Karwar and Bangalore had rainfall almost 300 millimeters above normal. This is only June 25th, remember. It's already remember. But in Kerala, almost all locations, or except few, are below normal. So to me, this is a classic situation which I discussed last week also. This is just shifted north compared to climatology. So Kerala's rainfall, orographic rainfall, is less for the last 20 years almost, except 1 or 2 extreme years. Okay. So this is what watching that this system will continue. That this is 300 members of one normal, and most of them are 1 or 2 are most below normal. And look at Wayanad, which had a huge rainfall last year. It was 200 meters below normal. And now, if you look at situation till 24th, this is the forecast for the month of June, made in May. You can see that it's not going to be very good because this whole region, unless something happens in the next 1 week to correct this, this forecast facial pattern is not very good. Okay? Something is coming out right here. But this whole unusual feature in which the rainfall went on this side, Rajasthan is twice the normal. Okay? But on this side, nothing came. So the question is, synoptic system didn't move across properly. I can't explain why only this side is a very rainfall. One little event in Jharkhand, which went well above normal last week, we discussed that. But this portion is very interesting. We'll see next week whether it changes. Now, this is all India rainfall, and you can see that last 3 plus 3 is 6, 9 so 1, 10 days has been above normal. That's why it made up for this deficit we had in the hiatus of the monsoon has been overcome. So, with the end of this month, I think it will be above normal, not well above normal. Okay. If you look at different parts of India, you can see that this is northwest, this is Rajasthan and so on. Northeast is normal. Central, of course, there's a system sitting on the around North Pole. And south, we had a little break period here, and then it has somewhat recovered. Okay. It's up to 25th. Now, this is my favorite graph. What is the forecast of GFS for the actual value? I would say it correctly predicted the decline of the monsoon intensity from 19th to 22nd, and also the increase. But today's rainfall, it got it wrong. Okay. Today, it predicted lower than normal, but actually it is close to 11 millimeters. Now, this is a special pattern for 1 day's forecast. I just was curious about it. 2 days, 18, it will continue to forecast of 28. This is the actual data given by IMD. This is the anomaly, unfortunately, not actual. But you can see that all these are correctly predicted where high rainfall occurred. 2 days ahead, they got the pattern correctly. What it is, I cannot, unless I add the actual values, climatology to this. Otherwise, it looks quite good. Okay. This is 2 days ahead. And this one was weekly rainfall. This is slightly different period. This is one day more. And I would say they didn't get this right. You see that week 2 forecast that we started on 5th June, they didn't get this part right. The moved out to Rajasthan was not captured. And this one more example, 1 day forecast for 19th, I would say is very good, except from here. You look, this looks very good compared to that. This anomaly is actual, so not so easy to see, but I would say broadly correctly predicted the region of high rainfall. Now, this is a forecast for the coming 2 weeks. So it continues to predict that ICC will sit over here, slightly weaken in the first week of July, and looks very similar here, not very different. So, so the good rainfall will occur in North India up to the end of June. That is the prediction. So June rainfall may go well above normal if that is true. And so next week we will see how accurate they are. Okay. Now this is the comparison between GFS and ECMW I show routinely, and the difference is here. This part is almost not quite, but this part is very different. In GFS, it's only confined to the Indo-Gangetic plain, but the ECMW went well into Rajasthan and also Pakistan. So I think this part was right in the forecast made by ECMW on 23rd June. Of course, this goes on to 8th July. We'll have to watch next week to see whether it's true or not. Okay, this is the other forecast from ECMWF showing that next week, 23rd, 30th June, system will be like same as GFS, it will be over Indo-Gangetic plain. It will continue to be there up to 7th July. So that is the forecast of ECMWF. So both GFS are roughly agree what time next 2 weeks. Okay. Now, the problem is that what IMD does, the so-called verification, is usually 1 year late. They take their time. They don't do it immediately. I would like to see it immediately. Maybe there are problems. So this is last year's, sorry, this is, 2024. This is the 18th July observed rainfall, categorized into 4 categories. Okay. This is day 1, day 2, day 3, day 4, day 5. Okay. Now, what surprised me about this one is there is no much difference. To me, between day 1, day 2, day 3, and day 4, only this Gujarat portion there is some difference. Otherwise, the pattern looks very similar. In terms of this category, not quantitatively, I don't see any improvement of the forecast on day 1, which I thought should be there. I thought day 1 should look very close to the observed, and as you go down, it should deteriorate. But I do not see a dramatic difference. I think this partly because of the way you do the categorization. Rainfall is a big headache. You can't make exact comparison. We know it will not be good. So you do categories, when you do that, it depends on how you do category. I'll give an example of what they have done. Yeah, this is a standard verification report published every year at the end of the monsoon. Okay, so this year will come up sometime in October. So, but the thing is, this is done for flood purposes, not for other purposes. So this is the so-called flood meteorological offices of IMD all over India. Okay, so there are all these offices. Okay, so next I'm going to show you the results from these offices, but don't go by the name. The Bangalore office covers entire Karnataka. Okay, all the rivers, the river basin forecast. Okay, relevant to flooding. But I don't understand I would have gone with every river basin separately, but for some reason, maybe lack of manpower, Karnataka covers all the river basins. Chennai, Madras one covers a very strange basin here, and Kerala has a very small region here. But North India has a very clear large basin. Okay, so let's say how the forecast done on river basins. Now they use the standard. You all know that way to compare the forecast based on the forecast. There's no compared to observe. Okay. So I'll just put it there for your benefit. Now, they're not doing it for a particular, they're going to all categories. So they divide rainfall into 5 categories, 0, 0 to 10, 11 to 25, and so on. Okay. So 3 plus 6 categories. So if you go along the diagonal line, you made the correct category. Okay. So you divide rainfall into categories and ask yourself whether forecast in the category was satisfied. Okay. So this percentage correct is some of these diagonal compared to everything total. So that's how they make their forecast. Now this is what they get. Now only thing I want to warn you, this is not according to the city. You know the city name. This is the headquarters of the office which gives the forecast. Okay, remember that. So it looks quite good to me. So river basin forecast by various officers, Bangalore the highest because I think covers a large region. Okay, errors are cancelling out, and Jabalpuri is the lowest in this list. But this is quite impressive that almost 50% of the time, IMD's forecast for river basins, not one river, a couple of rivers together, is right 60% of the time, almost 70% of the time, which I think is not bad. Okay, on day one, of course. As you go further, it will go down. You can see that in the report. Now, then they give the false alarm rate. That's also very important. You give a false alarm, heavy rain doesn't come. But I'm not happy about this thing. I see 100% here. That's very misleading. You know why? The heavy rainfall event is very rare. If you put all categories together and say I got 100% right for heavy rainfall, to me, there's not a correct way to categorize it. Because we all know that even today, heavy rainfall events, our ability to predict is poor, and the false alarm rate is very, very high. It's very poor. Okay. And again, there's a question of, I think, some definition here. See, if you look at false alarm rate, Herbert score is 0, not 1. Okay. You get you don't give any false alarm. But the way they have done it, it's confusing me. So I'm sure it's a question of how they did it. Secondly, if you put all the categories together, the high rainfall is so rare. I mean, you're getting it wrong also is rare. We put all of them together. So be careful to read the report. It's an interesting report, but this way of classification is somewhat confusing. Okay. And here is the full result, category wise. And to me, this doesn't look right. Yeah, this is correct. A high value means bad forecast. 0.7, 70% of the time you made a forecast which didn't happen. Okay. So that is the right thing. But it's much lower. Even no rainfall, they have a problem, although it's quite low. They get the best thing here, which is not surprising. We all know that models have problem with drizzle. They drizzle too much. Sometimes there's no rain, they give a drizzle. Okay. So the best in terms of false alarm rate is here, And in terms of direction, this is also the best. So this is a category where they come out with most of the time. So you can trust IMD to tell you it will rain a little bit quite correctly. No rain, you cannot trust. Very heavy rain, you cannot trust. Okay. Yeah, so I just want to end by pointing out that we have not had a radar in Bangalore now for a long time. We've been promised one for decades. But Mumbai has 6 radars. These 4 are urban radars. They cover a smaller range. And the website is very nice. You can look at it. You can watch when there's heavy rain in Mumbai. You can see all these nice patterns. And then there are 4 radars. You get a very good coverage. And this is established last year. Okay. In addition, there are 2 more radars which are bigger. Okay. I have a picture of that also here. Yeah. The ones which have a longer range, like one in Chennai, the bigger range one. But this is the most interesting. I hope IMD will establish such radars in every city, because this became essential due to climate change. Heavy rainfall events are increasing all over India, and Mumbai is the most famous because they got the 2005 event. So I think probably that triggered this establishment. I hope this will happen in every major city. But I think now they're next putting up one in Delhi because capital, and maybe Calcutta. I think Bangalore will come very late. But do you have any answer to that? Do they have any plan? Huh? No, urban radar I'm talking not. See, they are supposed to have regular radar. I don't know what happened. Urban radar, the smaller one, high frequency, no plans, right? Huh? Oh. Okay. Okay. I can tell you these radars are very nice. I can tell you that when they are there and they broadcast in real time, you can decide whether you want to go to MG Road or want to go to airport. You can watch the radar. Because over a short time scale, the rainfall systems are very predictable. I have done it in US. I look at the weather channel. The rain is going that way. I'd take a trip the other way. So I hope they'll do it. It's very useful for everyone. And I think today is not that costly, right? The smaller radars are not that costly, right? Huh? IITM. Yeah, this is IITM. Yeah. But it's a combined effort of Mumbai municipality, IMD, and IITM. It's a big called the Mumbai Missonet. You can look it up. Okay. Yeah, I'll stop here. And next week we'll hear from Sujatra. Okay.